Good morning. Good morning, everyone. First, I would like to thank the organizer giving me the chance to present our very preliminary result and thinking about how to make the collective emission of the excited surface phonon and the relationship between the excited surface phonon and the low energy nuclear reactions. I'm from Xiamen University. I'd like to thank Professor Xinzong Li and Zhongxun Tian. The two professors introduced me to this very challenging field. So Professor Li has raised a model he called resonant coupled tunneling model. So he used this model to fit the hot fusion reactions, and the three parameters model makes sense. Yeah. In this model, there's a coupled potential. One is Coulomb potential, as we know, and the other is the other potential in the nuclear region. So to make the total system, the total Hamiltonian as Ohmian Hamiltonian. So he assumed that the two potentials are both complex functions for the in the nuclear region. It has a real part. The real part should be negative, and the imaginary part is positive. But in the if the Hamiltonian is Ohmian, so the Coulomb potential should also be complex. The real part is positive, but the imaginary part is negative. So it's an amazing assumption. So how to prepare? So what's the physical meaning of the negative and negative imaginary part of the Coulomb potential? Physically, the negative imaginary part means it is emission state, just like laser. So how to prepare an emission state with input energy is a lattice energy, like outside the Coulomb barrier, and how the emission state resonantly coupled with the well in the nuclear reaction region. So actually, this very similar model exists in the optical region. So Maxwell equation and Schrödinger equation are very similar. Both of them are eigenvalue equation. In Schrödinger equation, we solve this equation. In quantum mechanics, we solve these equations. They are in Maxwell equation. With the potential is a dielectric function. There also some the tunneling effect, like here. We learn from how we can learn from the optical model in optics. Several people studied the nano optics property of cold-shell nanoparticle. So this is a naturally available material. Here is a gold core, and the shell is a dielectric material. Here for the gold, the real part is negative. Real part of the dielectric function negative, and the imagery part is positive. It means it's exhausted energy, absorption energy, right? Here for the naturally available material like cuprous oxide, both of the real and the imagery part are positive. But if we play a game, a mathematical game, assuming the imagery part is not positive but negative, it means that the shell material, the artificial image material of the shell material, it is not absorption energy but emission. So then we find that there's a resonance take place, and the extinction is significantly enhanced. So it means that actually the shell material here, the artificial shell material, is a game material, just like the game material in laser system. So it means that if the inner part and the outer part material have the opposite properties, then the tunneling takes place. So let's go back to this Professor Lee's model. Now the problem is how to prepare an emission state outside the Coulomb barrier. So Professor Higginson and Lett, they report that the phonon, the beating frequency, there's a resonant behavior between the beating frequency and excess heating. So how the phonon, the lattice vibration related to the excess heat. Then we calculate the phonon modes of the PdD system and the platinum hydrogen system. I should say that these two systems are very interesting because typically these two systems the vibrational modes are anharmonic. The anharmonic effect is very strong. This is a similar result reported by in the PIL. The dotted line is a harmonic model. So the potential is harmonic, and the solid line is anharmonic, and the blue for the palladium motion, and the red for the hydrogen or its isotope. So we find that the anharmonic effect is very strong. We also calculate the atomic chain model with palladium and the D2 system. If we change the position of this of the D2, we find that here is if it is the harmonic mode. This is if we consider the anharmonic effect, we find that all of these systems, the anharmonic effect is very strong. So anharmonicity effect in the PdD system is very strong. But how anharmonicity makes sense? So this is a model. For the palladium D system means the anharmonicity means the electron phonon interaction is also very strong, and furthermore, for the lifetime of the excited phonon state is also longer than the harmonic model, which may be beneficial to prepare the coherent state. this is the dashed line here is a harmonic model. So if we prepare a pair of potential. So here is a PD platinum D system. This is the real system here. If we approaching the a pair of PdD system, we find that the barrier here will be significantly reduced due to the anharmonicity. And in the middle part, it is a well. It is a well potential. Suppose it is the nuclear reaction state. So now we build the coupled model, model, like this. And this is the final state is here. So the anharmonicity makes the potential, the Coulomb barrier potential here significantly reduced. So the possible scenario, the strong coupled electron phonon interaction significantly lower the Coulomb barrier, and the localized mode here and here, the coherent and localized phonon pairs resonant coupled with the nuclear reaction state in nuclear well. So sorry. So 3 potential coupled, 1, 2, and here 3. The coherent and the localized mode here and here. Resonant coupled with the 3rd potential in the nuclear well. And the heat will also released by the lattice vibration. So that's why the low energy nuclear reaction, the condition of the reaction is very tricky, and the energy window is also very narrow. So first of all, you should make the reaction take place. Secondly, the heat should be released by the phonon, so it may destroy this reaction condition. So that might be why the triggering the condition is very tricky, and the reproducibility is ultra low. So the problem is how to make this reaction take place, how to trigger the coherent and localized phonon nuclear reaction coupled state. Our preliminary answer is pulse heating.
3 minutes left.
Okay, pulse heating. So we build a gel heating device. So he's a copper and he's a conducting layer, and we make the temperature increase speed. The heating rate is very high. This is the first device, and we use this device to prepare ultra small nanoparticles. And the second strategy is use the graphene oxide mediate pulse heat laser heating. So the graphene oxide absorb energy. We use the nanosecond pulse laser, and as we can see, the heating rate as high as 1 billion centigrade per second. So we use this method, we can prepare nanoparticle. The size is much smaller than 1 nanometer. Here is about 1 to 5 nanometer. So it means that it provides a condition, the confined condition to heat up the system very quickly. So next step, we would like to study some hydrogen-rich system like LA hydrogen 10. like this, and confine the system here, and then use a nanosecond pulse laser to heating up the system. And let's see how, and we would like to extract what's the reaction products. So many thanks for your listening. Hello?
Thank you very much. So just 2 minutes left. I can take 1 or 2 questions or comment. Short comment. Is there?
My hand's up, isn't it? You see my hand? This is Graham Hubler.
Yeah, I see you, Graham. Go ahead.
Oh, okay. Very nice work. I like your idea of pulse heating. I think that's a nice new wrinkle to this. Very nice. Your model, however, maybe you can tunnel and make the helium directly, but you still have a lot of energy to dispense with. So do you have any ideas on how you get rid of the binding, the 24 MeV of energy that's released? You're making helium with your tunneling model due to the anharmonicity of the phonon, but you still have the energy to get rid of the 24 MeV of energy. How does the lattice go from this point where you made the helium at a point, and how does it distribute that 24 MeV?
So thank you for your question. So here, just like here, we assume that it is just like the atomistic collision. So there's a many resonance states. So here, many resonance states. But which one will be effectively coupled with a potential well? That's the problem. We don't know which excited vibrational state will be effectively coupled with the well state. So we need to heating up the system to excite the vibration state from ground state to several excited state. Then that's why we try to use a pulse heating strategy. So I think that we can do many simulations and provide some theories, but after all, I think we need to establish some we need to build several experimental systems with high reproducibility. I think this system is promising to do so. So thank you for your question.